So as we're getting started this morning, I want us to take a look at the types of chemical reactions. I want to review those real quickly. I want to walk through the decomposition ones because there were several subtypes. And then I want to look at some examples and some rules about how to predict the products, and then we'll do some practice. Okay? So several of you, some of you have referenced that you're not quite sure what the different types are or what they mean. First one that we're going to talk about is synthesis, and you should have a copy of these notes already. So if you look back in your notebook, you should have this. Synthesis means we're going to create something, okay? And so we're going to start with two very simple, maybe elements, maybe simple molecules like O2 or H2O, and we are going to combine those into something more complex. So when you see two things that then turn into one, you got to say to yourself, oh, that was synthesis, because we took two items and combined them to make a single additional, to make a single product. Decomposition is the opposite of that. This is going to be when you start with one and break it down into two or more products. Now, I'm going to come back to this in a little while, but right now I just want you to get used to the idea that decomposition is to break those things down. We have several sub ideas here, and we will. Well, I'll tell you what, let's look at that now. Hey, several of you have said, hey, so I don't get this little sub idea of decomposition. All of these that I'm highlighting now, 1, 2, 3, 4, 5, these are all subcategories of decomposition. And you're like, oh, Mr. Willis, how am I supposed to remember all that? How do I memorize that? Here's the deal. You have to look for, I want you to follow the patterns, okay? This is not terribly difficult, but you got to follow the patterns, okay? Hey, here's our first pattern, carbonate. When you end up with something that's a carbonate, okay, hey, what's the chemical formula for a carbonate ion? Carbonate, CO3. Okay, carbonate, CO3. But what does that remind you of? CO2, carbon dioxide. Hey, guess what's produced? CO2, carbon dioxide. There's an additional oxygen which also combines with the metal. But what you need to recognize, if you'll just recognize, hey, a carbonate makes a carbon dioxide, then you can kind of look at what's left, oh, the metal and an oxygen, and put them together. And so these different decompositions, this is not like deep and mysterious. This is not dark magic of the universe or anything. You say, hey, what did I have? What do I think that's likely to turn into? What does that remind me of? And if you will look and learn the patterns, this will be much more straightforward than if you are like just trying to memorize that a metallic carbonate produces a metallic oxide and a carbon dioxide. Hey, write it down. You see the CO3, you see the CO2. Can you sort of visualize how one broke down into the other? All right, because that's all that we're going to do here. What's a hydroxide? Yeah, it's an OH. Okay, it's an OH. In this case, it's 2 because we had it bonded with copper 2, and so we needed a pair of -1s to balance the charges. So that hydroxide is actually going to turn into an H2O, which means 2 of those H's will go there, 1 O will go there, and then there's another O left, which ends up bonding to the metal again. So again, we have the metal with the leftover oxygen, just like we did up here, and the OH makes an H2O. Hey, so just look at, and you have this in your notes. I've already given you this, but you can be looking at it and kind of marking it. All right, hydroxides produce a water. Chlorates. Okay, hey, this is a little bit like carbonate, but it's different. Okay, chlorate, ClO3, is going to produce for us a chlorine. And so it's going to produce a metal chlorine and then some leftover oxygen, which will all bond together in pairs of O2. All right? So carbonate makes a CO2, hydroxide makes an H2O, chlorate, you've got that Cl that goes with the metal, and then some leftover oxygen that makes oxygen. Yeah?
Those going to be in the test?
Yes, these will be on the test.
So we have to say like the composition of metallic chlorate or something like that?
No, well, if I gave you this and asked you to predict or said decomposition of copper 2 chlorate, then you would need to be able to predict what it would make, balance it, Yeah.
Whether that's a good base.
Yeah.
Okay. So let's see. So let's look at what this would. So if we were to balance this, just kind of looking, I see a copper and a copper, and then I see one chlorine and two chlorines. But I've got two chlorines here, and then I've got 6 oxygens, and so I would just have to drop a 3 right here, and we would be balanced. Okay, and then I'm going to double check 1 copper, 2 chlorines, 2 chlorines, 2 times 3, 6 oxygens, 3 times 2, 6 oxygens. We're all good, we're all balanced. Okay? Other questions so far? Hey, I know I'm going quickly, but I just want to reinforce and show you guys the patterns again. Okay? Because if you see and learn the patterns, it's not nearly as hard as if you just try and memorize all the possibilities. If you try and memorize possibilities, forget it. It's not going to work. You're not going to be able to. But if you can look at the patterns, it's just like learning any foreign language. You look for the patterns. Okay? All right. Metallic sulfates. Ooh. So again, we've got a sulfate. All right. And so that is going to, this time we're just going to keep just like the chlorate stayed with the metal, the sulfur is going to stay with the metal, and then I'm going to have some leftover oxygens. Yeah, and if we just put a 2 here, that's going to balance it. All right, oxyacids. These are probably the most difficult, and I'm going to give you a little bit of leeway here if I ask you to do these at all. And here's why. Remember, when it says oxyacid, it means an acid that also has an oxygen-containing polyatomic ion. So here I've got sulfuric acid, or the hydrogens with my sulfate. That is going to break down into SO3. And you're like, how did you know it was 3? Why not 2? Why not 4? And that's a good question. Okay, and I don't have a strong answer for you in terms of how you can look and predict that at this point in your chemistry career. And so I'm going to give you a little bit of room in terms of that. But if you just look at what does it make, H2O, and then say, hey, what's left? SO3. Okay, sulfur trioxide. All right, because it's all nonmetals. Questions about, let's see, and then again here, take out H2O to make that water, and you're left with, with just that. Mr. Willis, I thought carbonates did something. That was carbonate with a metal. This is carbonate with a hydrogen because this is an acid. Okay? Hey, are there questions about those so far? I thought I saw a hand. No? No? Okay. All right. So those are our 5 decompositions. And again, I wanted to run through that because I wanted you to get to see that. Our third type is our single replacement. Hey, here's what I want you to see that all of these have in common, though. All 5 of those were decompositions. They're breaking down. You're starting with one thing and you're breaking into 2 or more others. 1 breaks into 2. 1 breaks into 2. 1 breaks into 2. 1 breaks into 2. You guys get the pattern. 1 breaks into... All right, there you go. Okay, a couple of us get the pattern. There you go. Hey, so that was the pattern for decomposition. Single replacement. This is where you have something that comes in alone, and then you have a compound, and then the thing that came in alone, if it's more reactive, will bump loose that one, and you'll end up with a new compound and a new lone ion. Again, that's where we're going to use our activity series in order to determine which is going to be more reactive. All right, real quick, double replacement. This is the most complex. Today, if I give you a double replacement, I just want you to say, okay, I'm just going to switch them. All right, I'll tell you a little later later this week or maybe early next week how to know if it's really going to happen or not. Okay. So today, if you see a double replacement, which is a 1-2-1-2, a 1-2 compound and a 1-2 compound, just say, oh, look, a pair and a pair, I'll bet they swap. And that'll be a double replacement. Last one that we'll talk about in this, next to last one, neutralization. Special type of displacement where you have an acid with the H, a base with the OH. Hey, an H and an OH, what do you think those might make? Water. Hey, an H and an OH. What do you think they might make? Water. Okay, no, you knew that. Okay, H and OH makes a water. That's H2O. You knew that. And so that's going to make the water. What's left? The A right there and the B right there, and they will combine together to make AB. Okay. So when it says salt, that does not mean NaCl. It means an ionically bonded compound. Any of your ionically bonded compounds with your metal, non-metal, those are called a salt. Not like assault, but like a salt. Okay, good. Hey, does that clear it up for you? Not really? Okay. Well, we could have, for example, let me just pick one here. We could have like hydrogen bromide or bromic acid, hydrobromic acid, and here let's say calcium hydroxide. All right, and I put them together, and the H and the OH. Woo,
that would be a CaOH.
Yeah, that's a Ca. Thank you, OH2. And so the H and the OH will combine to make water, and the Ca and the Br will form to make the salt calcium bromide. Okay, and sure enough, it'll have a 2 also. All right, questions about that? And so this is technically called a salt. All right. So let's roll on down and look at our last one, combustion. Combustion is pretty straightforward. It's going to start with CXHY. Those are some kind of numbers, C2H4, C6H19, whatever. But we've got some combination of carbon and hydrogen, maybe an oxygen on there, but usually just carbon and hydrogen. You add oxygen from the atmosphere, and that always generates CO2 and H2O. All right? So always makes CO2 and H2O in terms of the products, and then you just have to look at what the X and Y were in terms of getting it balanced. Okay? But your hydrocarbon always reacts to produce carbon dioxide and water, and also it produces heat, releases energy. All right? So with that in mind, let's just look real quickly, and we're basically going to review the same thing that we just talked about. All right. Hey, if something has carbon and hydrogen and reacts with oxygen, it's probably a combustion reaction. That'll make CO2 and H2O. So for example, let's just say that I have C6H 14, and I add some oxygen in there, and I'm going to make a certain amount of CO2 and a certain amount of H2O. And I'm going to look and I'm going to say, hey, there's six carbons there, which means I'll need 6 here. So carbon, carbon, check. Hydrogen's 14. Wow, 14. That means I'll need 7 over here.
What is that after the O right there?
A 2.
No,
That is also a 2.
Okay.
Let me clean that up a little. All right. All right, there we go. We'll make that a little thinner and easier to read. All right, so let's see, 6 carbons, 14 hydrogens, 7 times 2 is going to be 14. And then my oxygens. Okay, whoops, tough luck on that one with the 19. Okay, so sure enough, 12 and 7, 19. Don't have a clean way to get that. What I'm going to do instead then is I'm going to double this. Yeah, what you could do is you could look and say, okay, 19, that'll be 9.5. And then when you double it all to get whole numbers, that will automatically fix it for you. 2 times 6 is 12. Let me erase these so that we can... Let's see, 2 times 6 is 12. And then 2 times 14 is 28. So 14. And then 2 times 12 is 24 plus 14. Oh my gosh, carry the 1. 36. 38. Okay. All right, I'll take that, 38. Which means then I need, what, 19 here? All right. There you go. Hey, here's what I want you guys to see. That's a pretty oxygen-intense operation there. You got to have a lot of oxygen to get good combustion of that hydrocarbon. The larger your hydrocarbons get, the more oxygen-intense that's going to be. And then there's our products. Point being, that's a combustion reaction. So when you see that hydrocarbon and oxygen, that should say to you, ooh, combustion. Okay? So again, just combustion. Hey, 2 elements are very simple molecules. It's probably synthesis. Hydrogen and oxygen. And we're going to end up making water out of that. Okay, got to put a 2 there, got to put a 2 there to balance it. But again, that's synthesis. I started off with 2, I finished with 1. There you go. If you have something that has an arrow coming off of just one compound, like let's see, let's just say CaCO3. Okay, calcium carbonate. Let's see, carbonate's -2. Yes. And hey, if you've got one thing and then you've got an arrow, that lets you know it's going to be a decomposition. You look this up and you say, oh, wow, a carbonate. That means it's going to make a carbon dioxide and a metal oxide. Yeah. And again, you balance the charges and then balance the compounds. All right? So there's that.
Is that already balanced?
Let's see. Calcium, carbon, 3 oxygens, 1, 2, 3. Hey, what a fabulous day. Let's see. Pure elements. This is what we did yesterday. When you have a pure element plus another compound, usually, but not always ionic, but often, probably single displacement. but you need to look and see if it is, and see about the activity series and see if that's going to, if it's going to go or not. All right. Again, I'm just gonna pick KCl, at the dance, and in walks lithium. Wow, lithium. So reactive. And so you check the activity series, and sure enough, lithium is higher on the list than potassium. And so lithium will bump potassium. You'll end up with lithium chloride and potassium ions. All right. Again, only if your individual element is higher on the activity series than the replaceable element. All right.
How do you know if it's plus or minus or the K?
You have to look at your periodic chart and know how it forms an ion. It's if you replace the cation, it'll be positive. If you replace the anion, it'll be negative. Two ionic compounds combined, it's probably double displacement. Today I'm going to say, hey, it will be, although in the future I'm going to reference this note. This will only occur, that was bad. I need to switch to this will only occur if both reactants are soluble in water and only one product is soluble in water. We're going to talk about solubility probably on Monday, and so I'm not going to bother with that today. Today, if you see a twofer and a twofer, I'm going to tell you to switch them and just call it double displacement. All right? Like meaning, an ionic compound. And if you have an acid and a base, again, and I will use our favorite that I did just a second ago. Thank you. Or I didn't do this a second ago. I tried to avoid this, but I'm going to use it now. HCl plus NaOH. This is kind of the classic acid-base reaction because it's one of your stronger acids and one of your stronger bases. And again, we get water, H2O. And we get a sodium and a chlorine, which together makes sodium chloride. All right? And that is not only salt, but is a salt. So it's not only table salt, but it's also the chemical structure salt. Let's see, real quick, just for fun. That looks balanced. All right. Let's see. Questions about those ideas? Hey, I think that if you will kind of go back through those decompositions and look for patterns, and if you will use this set of notes that we got today along with the practice examples, I think that will really help you guys to be able to connect with some of this and help you to sort of find your way. All right. If that is still not working for you, then you can come see me and we can talk about, while you're working, and we can talk about what we need to. All right? So thanks very much.